So this talk is about how to understand what we are often seeing in today's society. We often see that the extreme ideas are coming in, not only in the politics, but also other topics such as healthcare choices. You know, the anti-vaxxers are everywhere nowadays, at least in the United States. And also food choices, vegetarian or vegan versus extremely meat eaters. So those are kind of the silly examples where we can see the rise of extreme ideas and opinions taking place in our society, the modern society. So the more recent examples include COVID-19, of course. So there are the lots of people who just want to ignore it and just live, the normal life without even wearing any masks. And there's another camp that everybody needs to lock themselves down completely. So we shouldn't do anything there. So that's kind of two extreme opinions coming up right now. And we are witnessing the very severe fight between those two extremes. So the society is divided in terms of opinions and ideas. So the questions I would like to address in this highly theoretical computational work is, are they really trying to go extreme intentionally? So could it be another approach to understand their behavior so that they are just trying to conform to each other, which is very natural in our society? We are, after all, social organisms. We want to blend in. That's nothing related to the extremization of our opinions. But this might be another alternative explanation, especially if our society is inherently driven to get organized into social bubbles. So that's the main research question I want to address. Or more like this is the point I want to make by demonstrating, by creating an operationalized computational simulation model. So here in this research, the objectives are to develop an agent-based model of adaptive social networks. And the key ingredient in this model is are four things. One is social conformity. Everybody wants to blend in their social neighborhood. They want to become the same. And also homophily. They want to hang out with similar-minded people. These are very natural and very strong social behavioral tendencies that there are many documentations about those. And counter to those two mechanisms, I also include attention to novelty. Some people are seeking for new ideas, new opinions, something that is not quite the same as a social norm. So that's what we call here as attention to novelty. And finally, the random fluctuation is kind of whimsical thinking. So occasionally you can actually come up with different ideas, and that creates temporal fluctuations of opinions in each individual brain, so to speak. And we conduct a large-scale systematic simulation to sweep the parameter space to study the effect of each of those key ingredients on the final outcome of social evolution. The framework I'm using is adaptive networks. As some of you may already know, this is the family of dynamical network models in which both node states and the link topologies are co-evolving with each other. So this is a famous example of the karate club network. Initially, it's split into two different camps between one guy and another guy leading the bunch of people. And here's a hypothetical simulation. If you run the social diffusion process on this karate club network in which the cultures or ideas are going to diffuse through the social links, but the social link weights also get changed because of the similarities and differences of the ideas in each node. Sometimes eventually you might see the network splitting like this. Okay. All right. So I see some comments coming up in the chat window. I will answer to those questions after the talk. Okay. So here's a mathematical model that we are studying in this paper. It's a very simplistic, almost pseudo-linear dynamical equation model. So each node I has the state variable x, and that changes based on this very simplistic linear dynamical equation. So basically this x, bracket x, is a social norm. It's a weighted average of other people's ideas within the social neighborhood, and you try to approach your social neighbor's norm with the parameter C. And this is the random fluctuation term. And the edge weight also changes based on two mechanisms. This is the anatomy of these equations. This is the social conformity. This is the random fluctuation. And the two terms included in the edge weight dynamics is split into homophily that promotes the edge connections between similar-minded people, and attention to novelty. This is based on the difference of one of your neighbor's ideas to the average in the social, the neighbor states. And to run the simulation, I use the simplest possible mathematical form. In this case, it's almost linear. It's a linear function of the difference of states. So this is the functional form of the homophily adaptive edge weight effect. So theta h basically determines the height of the peak value here. And as the difference between your state and your neighbor's state gets higher, this term becomes negative. So basically you hate people who don't have the same opinion as yours. And this is almost opposite. This is the attention to novelty. In this case, this is a function of your local social norm, not your own state, but the social norm and one of the neighbor's state. If the neighbor's state is very different from the social norm, you may want to pay particular attention to his or her opinions. So it's almost a symmetrical functions, although they are not exactly the same, because the attention to novelty is a function of the social norm. So here's some demonstration. I try to take a risk to run the live simulation here. Hopefully this is going to work. Yeah, here you go. Yeah, this is one example. It's running in my laptop right now. You see initially the topology fully connected, but the link weights are random, and so are the node states. Under the given parameter setting, by the way, don't pay attention to these extreme edges. So these are just coming from the instabilities of Spring embedding. So after several steps, you see the nodes tend to self-organize and self-sort based on the value of opinions. And this is because of a homophily. And also, even though they are trying to blend into the local social norm, self-conformity, social conformity is in place. But eventually, you start to see some extreme ideas arising because of the random fluctuation. And the random fluctuation also pushes opinion to the edge of the network structure, and eventually they might get disconnected. And here you see the continuous spectrum of the many different opinions, but eventually, in this particular simulation settings, networks are going to get pretty much fragmented, I believe. And I can actually change the settings. I'm even taking the more risks by changing the parameter settings of the code right now. Hold on 1 second. Let's run this one more time. I just changed parameter settings. I hope this will give you a different picture of the same model. I decreased the homophily coefficient and increased the attention to novelty. So let's see how this behaves. Again, this is coming from the instability of the Spring embedding. So this is nothing different from the rest of the world. But you see that the dynamics is completely different. Everybody gets more and more connected, and everybody has pretty much a similar kind of the ideas, because in this dynamical settings with the changed parameters, if someone said something a little bit different from the social norm, that person receives the particular attention because everybody is looking for new information. So he or she will be connected back to the normal, and the idea diversity is lost. Now you see most of the ideas are very much like a yellowish color, including this guy also. And then network is very strongly connected. So this is one of the illustrations, the different outcomes you can expect from this type of the model. So I'm going to continue. Okay. So I just showed you two different extreme results. So it's known that in this kind of adaptive social network model, there are social fragmentations possible. One is that the society is fragmented with only very small clustered communities, each of which has totally different opinions. So in this case, diversity of opinion is maintained, but the connectivity is lost. The other extreme is that everybody loves each other because they are the same, similarly minded, and network is heavily integrated, but the idea diversity is completely lost. So we explored these two extremes, how each parameter affects the social evolution. So here's some details. We tried several different network sizes from 30 to 1,000, and the parameter values, the strength of social conformity, homophily, attention to novelty, and the two parameter values inside the homophily and attention functions in a logarithmic scale from 0.01 to 0.03. And this is time duration. And for all the possible combinations, we ran at least 5 replications of independent simulation runs, except for the largest network size. This is a monster. It takes like 4 and 5 hours in my poor laptop. So I could only run only one case for each parameter combinations. So this is the total number of the simulation run we did. So for each simulation, we need to measure the topological and state outcomes. So in terms of structure, we measured these 3 quantities: the average edge weight, number of communities after applying the modularity maximization method, and how much modularity was achieved. So in these 2 extreme cases, 3 quantities listed here should show low, high, and high if the society is fragmented, or high and low if the society is integrated. So this is about the structure. In terms of the distribution ideas, I took 2 very crude measurements. One is the range, or the difference between maximum value and the minimum value of average community states. So this means that the first you identify communities, and then within each community, you calculate what is the average culture established in this community, and then take the maximum and the minimum. And the other way is the same value, but standard deviation. So in the first scenario, the fragment society should have high and high values for both of them. The other extreme should have low and low. So we are looking for these profiles. If these 5 measurements take low, high, 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 and high, then we know that the society is fragmenting, or vice versa. Okay, and we ran like 16,000 simulations. Here's the results. And this is kind of confusing because here I see, I plotted the horizontal axis, which is the choices of parameter values in the logarithmic scale. And one of the reviewers got confused because here, this is a linear fit, but the linear fit is curvy. So I was very much criticized for doing something wrong. But if you are the reviewer, you don't have to disclose yourself. But this is working fine. It's a linear, simple line fitting applied to the simulation result, but simply for the visualization, I use a log scale for the horizontal axis. That's why you see the curves. But anyway, so what you are seeing here is the effect of each of the model parameters swept in the logarithmic scale, and how each parameter affects each of the structural outcome measures. And you can clearly see that there are 2 parameters that show the clear trend that as we were expected. The H is the strength of homophily. If people want to connect to the similarly minded others, it actually promotes more fragmentation because the first one goes low, second and third goes high. And then counter to that, the attention to the novelty parameter A actually shows the opposite effect. That if people seek more new, different ideas, society tends to get more aggregated, more connected, and the fragmentation is suppressed. And this is about the structure. And in terms of the idea distribution, this continues. Again, H and A has the strongest and the most significant effects on the idea range or the standard deviation. Again, the H homophily promotes fragmentation and the diversification of ideas. The attention to novelty suppresses the diversification of ideas and it maintains social connectivity. And this is kind of interesting results. So we also conducted the more traditional statistical regression analysis to study which parameter is strongest in terms of effect sizes. So here you are seeing that the result of multiple regressions of each model parameters and their interactions on each of the outcome measures. And here you see that the numbers really means that the effect size. And if you choose the largest and the second largest effect sizes on the linear term, turns out, again, H and A are the two most significant parameters that affects in completely opposite direction. H promotes fragmentation, A promotes integration. So this is kind of summary of what we got so far. To conclude in this presentation, what we discovered was homophily, the people's tendency to hang out with similar-minded people, it actually promotes escalation of ideas at the cost of social connectivity, even if people just want to blend in to others. So they have no intention to extremize their opinions, and yet they just want to hang out with others, and then that actually promote the self-organization, self-escalation of idea in society. And opposite to that, if people want to seek the new ideas from their social neighborhood, it actually promotes the social integration, and yet the idea space is getting narrower and narrower. And this actually gives us a very interesting paradox between microscopic behaviors of individuals and macroscopic outcomes. If the society, if the individual seeks sameness, then society produces diversity, ironically. Or if the individual seeks diversity locally, and the society actually reaches sameness. So this is a conundrum. What kind of behavior we should choose if we want to achieve something at the societal level? So here are the implications. How can we utilize this kind of really puzzling conclusion coming from this theoretical model for consensus, agreement, or innovation or creativity? And this, I think, depends on the context. For example, what if we want to achieve scientific discoveries, progress of science? What each of us as researchers need to do? Should we actually read more literature, which is basically collecting more information, try to seek the social conformity to jump onto the similar fashionable topics? Or should we just stop reading and do whatever we want to do? Or policy making. Policy making requires the good level of consensus. In that case, fighting against each other by using the political party, this may or may not be the good idea by looking at the results of these simulation models. And finally, we are all in the COVID-19 situation. What would be the best way to promote the discovery of solutions, either cure or vaccine or any other political, social, epidemiological intervention strategies? What would be the best strategy as a whole, as a society, to fight with this COVID-19 pandemic? I think there are lots of things to think about. So the model is very much limited. We didn't consider much of the nonlinearity in the functional forms. And all the agents behave the same way. There is no heterogeneity. So that's something we really need to include. And the parameter range we swept is also very narrow. To do all of this, we need more computational power. This is actually the picture of the recently top-ranked supercomputer, Fujitsu's Fugaku. It's now ranked in the first place on the top 500.org. I really need to have access to this kind of computer. Anyway, so I thank all the funding sources that support this research from Waseda University, Kakenhi, and Max Planck Institute. And just a shameless plug in the last minute, there is another paper published recently about a very similar topic at the Physical Review E. This model is not about networks, but it uses partial differential equations to show how disagreement is going to grow if people have access to the larger size of information. If you are interested, please take a look. It's open access. Thank you very much. And this is the picture I took when I was working on this model at Max Planck. Thank you very much.
Thank you, Hiroki. Thank you very much for your presentation.
Yep.
Very, very nice, very interesting. So I guess we can open the session for question and questions. I think most of them are on the chat, so.
Okay, should I just read the chat window?
Sure.
Okay, so let's see.
Green Bao was the first person to ask something directly to your work.
Okay, so the first question is, I'm trying to find whose question is the first.
Hongling Bao.
Only Bao, okay. Yeah, it'll be interesting to also study the clustering coefficient from a structure perspective. Yeah. Yes, absolutely. Yes, clustering coefficient in this scenario, the network itself is very much clustered from the beginning because we simulate essentially the fully connected networks. So we need to generalize the definition of clustering coefficient into a weighted edge version. But I think in this case, the conclusion is very much consistent with the other measurements shows. So homophily tend to increase the clustering coefficient, and especially because connection is getting lost. The connection you will have is most likely the connection among your very tiny localized clusters. But the other extreme is also possible. If the attention to novelty brings everybody together, the clustering coefficient also comes really high because it's basically fully connected complete graph. So maybe my guess is the clustering coefficient may show this kind of U-shaped curve. Okay. Next question from JT. Thank you very much. So how should I relate homophily and attention to novelty in this model with flocking in animals? Okay. This is something I didn't really think about. So in general, many of the animals that show the large scale flocking behavior, they are very similar to each other. And they don't really distinguish which individual they need to move into. So closer to each other. So in that case, homophily may not be so actively playing roles. But having said that, the self-organizing sorting behavior that I showed in the real-time simulation, similar kind of self-sorting behavior is already very well known in the famous paper by Ian Cousin and his colleagues, 2003. He studied the spontaneous self-sorting of fish schools based on the behavior parameter differences. So that might be somewhat related to the self-organization process as we saw in our simulation. Okay, and the next question from Oscar. The values of homophily attention of novelty should be part of the state of each. Yeah, exactly. Yes, this is exactly what I want to do in the next step. So if you include those parameter values as individual properties, then and then put some distribution, and then the result of the simulation will be quite different. And in fact, we actually have another publication that was out earlier this year, which is not using exactly the same model, but we also had the cultural integration model. And that was published in NetSciX proceedings earlier this year. The short answer to that question is, if the behavior parameters are diverse inside the society among agents, networks can actually maintain both idea diversity and the structural connectivity. Because some people actually start to play the role of being a glue between, Republicans, Democrats, for example. So there should be some people who are, more tolerating the cultural differences. If they do exist in society, it's not just a pure fragmentation or integration. There should be another option also possible. Thank you very much, Steen. And Susan, novelty appears to be along a single dimensional ideas. Yes, so in this case, the idea space is limited to the only one-dimensional space. So my guess is that if you start considering a multi-dimensional idea space, the novelty or the self-sorting might actually start to move to the multi-dimensional different directions. So that is definitely a possibility. Although the definition of novelty is still the same, it's just a difference between your social norms. Could be the point in the multidimensional space and one idea. You can measure any distance between those 2 points. Okay, and the other question from Mike. Expand on why increased attention to novelty narrows the diversity of ideas. Yes, I know that this initially also was very counterintuitive to me. And there are some subtleties here. In this particular model, the attention to novelty always try to reconnect yourself to somewhat deviant ideas in your social norm. So if someone says something a little bit different from the other friends in your social neighborhood, that person is more integrated into the network, and that basically kills his or her ideas down the road, because he is also practicing social conformity. And if we try to bring that person back to our gang, we are basically making him or her into our color. So the color is always blending in the bidirectional way. So the attention to novelty is suppressing anyone who is standing out. It is actually reintegrated and brainwashed. This is actually a very bad way to say it, but that's the one of the explanation why the attention to novelty narrows down the diversity. Thank you, Peter. And Dabri, from the sample videos, that was actually not a video, it was a real-time simulation. Okay, 2 clusters, yes. What do you mean by clusters? Can you unmute and elaborate more on this question? Dabri, are you here? Hi.
Yeah, I mean, it looked like you just have 2 opposing states or views, or whatever you call it. Can you have more of these? Like,
yep.
Or it's because it's on 1 dimension, then they can only be 2.
Yes, exactly. So, but actually, it's actually not. So even though it looks like it's stretching into the 1-dimensional space, eventually the string or spectrum of opinions is going to fragment into a bunch of pieces. So one cluster here, another cluster here, but in the middle of the opinion, they also tend to, disconnect from their neighbors. So eventually we're going to get ending up with seeing so many different clusters. And this will become more manifested if the opinion space will be multidimensional. That's probably what's going to happen.
Oh, so that's like slide 11. You have almost every individual is a separate cluster, basically.
Yes, in this case, this is the extreme case. Okay. Basically, everybody hates each other.
Okay.
Yeah. Okay. So, okay, let me address relationship to Schelling result. Yeah, Schelling result is about the homophily in terms of spatial location. So you could consider this as a networked version instead of geographical distance as used in the Schelling's model. Okay. But also Schelling's model does not really allow agents to change their state. It was either black and white or red and blue. But this model allows you to change your property. So that's another difference. That makes the system co-evolutionary. Okay, and Steen, how to verify your, my result to the formation echo chambers. Yes, I would say this picture that you are seeing on the left, this is a bunch of echo chambers. In this parameter setting, this is a little bit too extreme. So each echo chamber is 1 person. But if you relax some of the constraints a little bit more, you start to see the small clusters forming, and then they are disconnected from each other. And then each one of the cluster have a very homogeneous opinion state inside. And that's actually the one explanation how echo chambers form. The echo chambers are primarily driven by the homophily principle. Nowadays, we have lots of power to preferentially choose what kind of information source we want to get in social media and even other public media. So if we have the right to choose which information we want to hear more, then it naturally leads to the formation of many echo chambers.
But I'm thinking, could you would it be possible for you to actually use data from? Yeah, I guess it's difficult. It'll be difficult to get it from the platforms. But have you thought about you finding sort of empirical data and then?
Yeah. Yes. So the data are actually abundant in terms of the network evolution. One of the examples I showed, it was the classical example here. This one, this picture is actually the Twitter data. And you can make a guess what this is. This is about the political opinions. And the Democrats and Republicans, and they spontaneously segregate. So this is kind of large scale echo chambers. And you can obtain similar kinds of the social media data on the variety of topics. What's really difficult to get the data about is the opinion state. So if you want to study the co-evolution between structures of the node state, we need to have the other side of data, which is extremely difficult to get. So we have been struggling for the last 3 years to how to get the right kind of empirical data to test this kind of results. And Twitter does not release the content data anymore. And there are many other online data sources, but it's very difficult to extract the opinion state from the natural language. There are many machine learning techniques available that we are using some of them, but still it's a very non-trivial time-consuming process.
Yeah, thank you.
Yeah, we are working on it. Thank you.
Great.
Okay, final question from Susan. So what happens with high novelty, attention to novelty, low conformity? You know what, we can try it. I have no idea. So low conformity. So let's make the conformity 0 and the homophily should be 0 and high novelty. So this could be, yeah, this is the condition. The good thing about simulation study is that we can run an experiment in front of the audience. I have no idea what's going to happen. Run. So this is a condition where there is no homophily or social distribution. And everybody wants to get connected to someone who has different ideas. And then this is kind of boring. Everybody becomes friends. But there is no conformity. So ideas remain the same. So this is like a Republican Democrats talking to each other very friendly at the bar, which I don't think is going to be happening in reality. But we can test some of the hypothetical scenarios like this. Okay. I think that's it. Yeah, I agree. Friends, but diversity, great. Thank you, Susan. So thank you very much. So I think that's the end of, okay, thank you, Jan. So, okay, that's it for my talk.
Thank you, Hiroki. Thank you very much. I guess that if there's no other questions, I think we may want to go to take the 10-minute recess and come back for a discussion session. I just want to say to the presenters that they have wonderful work. Really, thank you to all of you. Okay, and well, I don't know if Alex wants to say something more about what's coming up.
Yes, please. So yeah, thank you all of you. That was really interesting stuff. So I just want to put up the questions again on the screen that we've just got for framing discussion. There's a lot of materials on the Slack channel as well. So if I just share my screen, I can work out how to do it. Now I can't see how to, there we go.